This is Objective 2 of Section 1.6. This video is about limit laws, one-sided limits, and the old squeeze play. Some limits are best calculated by first finding left and right-hand limits. The following theorem says that a two-sided limit exists if and only if both of the one-sided limits exist and are equal. So there's the theorem. Okay, we are able to say that we've got this limit here if and only if the limit as x approaches a from the left of f of x equals the same number L that is equal to the limit as x approaches a from the right of f of x. When computing one-sided limits, we first use the fact that the limit laws also hold for one-sided limits, the limit laws. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limit. The limit of a product is the product of the limits. And a few others. Remember the greatest integer function. It is defined, okay, there's that symbol, it looks kind of like brackets, which in a calculator, in a TI, is int x. Int x. And it's the largest integer that is less than or equal to the input. So the largest integer that is less than or equal to 4 is 4. The largest integer that is less than or equal to 4.8 is 4. The largest integer that is less than or equal to pi is 3. And the largest integer, which is less than or equal to the square root of 2, so we're talking about the largest integer which is less than or equal to a number which is about 1.414, is 1. And the largest integer which is less than or equal to negative 1/2 is negative 1, right? Integers, those include the negatives, so the greatest integer function returns negative 1 for an input of negative 1/2. Show that the limit as x approaches 3 of the greatest integer function evaluated at x does not exist. Okay, so there's the graph of the greatest integer function, kind of a famous step function if such a thing exists. The graph of the greatest integer function is shown in figure 6. Since the greatest integer less than or equal to x equals 3, for x between 3 and 4, okay, so x is between 3 and 4, and x is approaching 3 from the right, and that limit is 3. Okay, x is between 3 and 4, and it's moving over there. Then we have to say that the limit as x approaches 3 from the right of the greatest integer less than or equal to x is 3. But if we approach 3 from the left, the greatest integer less than or equal to x is 2 in that interval. And so those two limits are different. From the left it's 2, and from the right it's 3. From the left of 3, approaching 3, the limit is 2, but from the right it's 3. And so because these one-sided limits are not equal, you know, there's no L like we're supposed to have in that theorem, the limit as x approaches 3 of the greatest integer less than or equal to x does not exist by theorem 1. The theorem said that the theorem that said that the two one-sided limits had to be the same and they both had to be equal to the same number L. The next two theorems give two additional properties of limits. So here's a theorem. You've got f of x less than or equal to g of x. Now, in your mind, you see a graph f which is below another graph g in the plane. If f of x is less than or equal to g of x, when x is near some number a, except possibly at a, and the limits of f and g both exist as x approaches a, then we have to say that the limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. Okay? Now that's not a big news flash. You know, we look at that and it seems trivial, and we're tempted to look for something, you know, that we're maybe missing. But we're really not missing anything. And so we've got this squeeze theorem. Now we've got three functions. F of x is less than or equal to g of x is less than or equal to h of x. Okay, and so we can kind of see the three graphs. We'll look at a picture like that in a moment. When x is near a, except possibly at a, right? Limits don't care about at a, only near a. If it happens to be true that the limits are equal, limit as x approaches a of f of x is equal to the limit as x approaches a of h of x. Okay, and so we know something about the limit of f, we know something about the limit of h. We're still not saying anything about g, but those two limits are the same. Call that value L. Then the conclusion is we can also say that the limit as x approaches a of g of x is equal to L. Okay, so here's the picture. The squeeze theorem, which is sometimes called the sandwich theorem or the pinching theorem, or the old squeeze play, is illustrated by figure 7. Okay, so g, you know, it had to be, g of x had to be L as x approaches a. The limit as x approaches a of g of x had to be L, because that's what it was for h and f, and g is squeezed between f and h because one of the conditions of the theorem, the squeeze theorem, is that f of x is less than or equal to g of x is less than or equal to h of x. It says that if g of x is squeezed between f of x and h of x near a, and if f and h have the same limit L at a, g is forced to have the same limit. That's the old squeeze play.